Hello, and welcome to Little Buddies Physics. Today we will be learning all about centripetal force.
I'm Chelsea.
And I'm Logan. The first question we have to answer is, what is centripetal force?
The dictionary definition of centripetal force is a force that acts on a body moving in a circular path and is directed towards the center around which the body is moving.
Okay, but what does that mean in simple English?
It is the force that keeps an object moving along a circular path. What are some examples of real-life things that centripetal forces act on?
Well, I can think of a Ferris wheel, or on a racetrack, or the planets in the sky.
So, there are two equations for centripetal force. The first one is mv squared all over r, or the object's mass multiplied by its velocity squared, divided by the radius of the circular path. The second one is f of c equals m times a of c.
Okay, but what does the a sub c stand for in the second equation?
Excellent question, Logan. Well, a of c stands for centripetal acceleration.
Centripetal acceleration, also called a radial acceleration, is the acceleration of an object moving in a uniform circular motion, resulting from a net external force.
Centripetal acceleration is always pointed toward the center of the circular path. Without centripetal acceleration, the object would not move in a circle.
Why is that?
Well, Newton's first law, an object in motion will continue to move in a straight line unless acted upon by an external force. In this case, centripetal acceleration is what changes the direction of the object.
Neat. So how do we calculate this?
The equation for this is
velocity squared all over r, the radius. This may sound familiar, and that's because it's part of the first equation for centripetal force, mv squared over r.
Now time for a quick demonstration. Here we have a balloon attached to a string, which Logan will spin around in a circle. But let's break it down a little to explain what's going on. Here we have the balloon in mid-rotation. When the balloon is moving, the string is pulled on, creating tension. The tension of the string acts as the centripetal force, keeping the balloon moving in a circle. If the string were to be cut, which would remove the centripetal force, then the balloon would go flying off in the direction that it's moving. Here's another demo. As the balloon is shaken, the penny is pushed into the walls of the balloon. The balloon in turn pushes back against the penny, which causes the penny to move in a circular path. Unfortunately, the penny is moving so quickly that it's hard to see in the video. But if the balloon was popped, there would be no centripetal force keeping the penny in circular motion, so it would go flying off in the direction of its velocity. The penny would continue to spin forever if friction and gravity did not act upon it.
Now let's return to those other real-life examples. In a Ferris wheel, the centripetal force causing the rotation is a mix of gravity and the normal force.
But what exactly is a normal force?
Haven't you ever heard of Newton's third law? Every action has an equal and opposite reaction. The normal force is the reaction force in this case, and it's what prevents two objects from phasing through each other when they collide. Anyways, back to our examples.
When a race car is moving on a circular track, the car experiences a centripetal force. The centripetal force is caused by the friction between the car's tires and the road. Without it, the car wouldn't be able to turn at all.
The planets of our solar system move around the sun in an orbit, or a circular path. In this case, the centripetal force moving them in their orbits is caused by the gravitational attraction between the sun and those planets. Whoa! That was terrifying.
If you want to learn more about energy, be sure to check out our next video.
And don't forget to like and subscribe for more educational physics videos.